Assalamualaikum warahmatullahi taala wabarakatuh. May peace and blessing of God upon all of you. Selamat tengah hari and good afternoon. Um, Today we're going to look at the new topics on governing equation of motion. Is part of the kinetics of motion. Right, as usual, in order for us to look at the kinetics problem that can be solved using the force, mass, and acceleration relationship, we had to look at a system that can be modeled as a particle, right? So this topic is covered in the Professor Merriam book in chapter 3. And the governing equation is based on the Newton's second law. The Newton's second law says that the net force acting on the body has a relationship with the ability of the system to resist motion, which is the mass, and also has a relationship with the accelerations. And from that, we can produce an equation of motion. Here, we don't see any names, right? So we just say that is a governing equation of motion. This one is applied to the particles or system of particles or to a rigid body or to deformable bodies. So this is the equation that we're going to use for a particle, for a system that we model as a particle. Right. For particle, normally it has only one type of motion, which is translation. Right. So the translation can be divided into two: rectilinear motion and curvilinear motion. So rectilinear motion means the particle is moving in a straight line, right? And from the Newton's second law tells us that the force and the acceleration is the vector quantity. It means that it has magnitude, it has direction, and it has the origin, right? The origin of the force. So there is a disagreement when we try to represent the vectors representation. So in the Professor Hibler books, the way that we represent the body forces is different compared to the Professor Merriam. But most of the vector quantity are they are agree on certain convention on the way to represent these vector quantities. Right. So if you look at this equation 3.5, immediately there is a step that is not been mentioned to you after we model the system as a particle. Here they don't mention about the frame of reference, right, where we define the coordinate system. So for rectilinear motion, if we identify the particle having a rectilinear motion, the next step is to identify the coordinate system. So we need to know the origin of the coordinate system. And then, and this origin of coordinate system usually is placed exactly on the body of the system of the particles. So for the force and the accelerations, the coordinate system should be placed on the body, on the particle, right? So based on this coordinate system, we can have all the net force in x direction, y direction, and z direction. And in our course, normally we consider a plane motion. The system are moving, move in the plane, in vertical plane, and we can also get the acceleration vectors and its magnitudes, as well as the force and the direction and its magnitude. Now we look at the second translation motion for particles. So in this translation motion, the generic form is curvilinear motion. So this curvilinear motion can be represented by three coordinate system, which is rectangular coordinate system, spherical coordinate system, S coordinate system, tangential coordinate system, and circumpolar coordinate system, right? But in the book, they just emphasize on two coordinate system, and this is the rectangular coordinates, right? So we have to define the coordinate system, rectangular coordinate system, and the figure next to it tell us about the position of the coordinate system that need to be placed, and then the location of acceleration vectors. So this is the thing that we have to so far for this curvilinear motion, because we are looking at the topic centric, right, situation, we just consider only the acceleration. Next, let's look at the way that we can solve the curvilinear motion is to use normal and tangential coordinates. So in the normal and tangential coordinates, there is an xy there, but we don't specifically state the x and y component, but we just have these axes. So for the normal and tangential coordinates, we can find that the way that we're going to represent that is based on the one on the right, where we make sure that the point A and A prime is coincide, and from that way of representation, we can then evaluate the normal acceleration and tangential accelerations. And the normal accelerations component is equal to velocity at A, right, divided by the radius of curvature. And for the tangential, the absolute values, the tangential component is given by the V dot, right? So that's the way that we define how we can use the equation. Now the equation has been written in the normal tangential coordinate system. The one that I mentioned before, the equation of motion, right, has been written in the normal and tangential coordinate system. So we have to identify this coordinate system when we try to solve this problem. Next, we should look at another curvilinear motion, but we represent the motion using the polar coordinate, spherical polar coordinate system. And then we can look at the equation of motion have been rewrite in this coordinate system. So we have the force in acting in the radial direction and the force that acting in angular directions. Similarly, we can have the same expression for accelerations. So the radial acceleration is given by the the radial accelerations minus the r theta power of 2. If you look again on the um, for the normal and tangential direction, R is represented by radius of curvature. So we have for system in these problems, the radius of curvature is the distance from the um, origin of the coordinate system. So on the right hand side, we can we know the values of the radial location. So we need to use the position vectors to define the position of particles. Similarly, we can have the definition for tangential angular accelerations. So we have two components there. Um, so this is the way that we can use the polar coordinate to solve the equation of motion. Right. So this is the conclusion that the Professor Merriam had concluded from this topic. So if you want to apply the equation of motion, right, well, we want to solve the equation of motion. First, we have to model the problem. So you have to model the problem as a particles. Next, we have to identify the motion. Is it a rectilinear motion, or you just use one rectangular coordinate system, or is it curvilinear coordinate system? And if we know the curvilinear coordinate system, then curvilinear motion, then we have to identify one of the three coordinate system that is proposed, right? After we identify the motion, you can then choose the most suitable coordinate system. And this one require experience. So if you do a lot of exercise, then automatically you can naturally know what is the best coordinate system to solve that problem. And then this is very important because when we identify the coordinate system, we can provide the expression, mathematical expression of force and acceleration, which is consistent with the coordinate system that we use. So the author also gives examples. So if we are using a normal tangential coordinate system, the positive value is always towards the center of curvatures, the center of rotation, something like that. And then the positive sense for the normal forces is also towards the center of curvature. And the positive acceleration will be on the normal acceleration. Then we need to draw the free body diagram of the body. And then after that, we can get we write the equation of the equation of motion. So in this topic, particles, when I mentioned about this frame of reference or coordinate system, for particle, it has a wide scope compared to the rigid body. Even though not in terms of the system, the particle can but it's only limited for translational motion. The scope is greater in terms of evaluating the equation of motion based on the initial frame of reference and non-initial frame of reference. What I mean by non-initial frame of reference is that the coordinate system is moving, right? So in the rigid body, most of the cases is limited only to the initial frame of reference. Previously, in the course, we're not going to cover that because one of the course outcome of the course is for the student to provide the kinematic and kinetic description of problem for a rigid body motion. So indirectly, it tells us that you are going to look at the initial frame of reference